Good morning, everyone. First of all, I would like to thank the organizers for this invitation. It's a great honor and it's a pleasure to be here. And thank you, Hans-Peter, for the nice introduction. Let's start with a satellite image of Europe. Excuse me. So looking from space of Europe, you can see two things. First, it looks like that there's almost no human influence. The whole continent is more or less covered by a kind of green biofilm. And the second thing that you can see is there are no freshwaters almost, except you see some freshwaters in northern Scandinavia and some here in impounded sections on the Volga. We know that both is not true. So we need to have a different view on Europe, and we can have the same view from satellite image during another time. And you all are aware about these pictures during night, where you see this huge human transformation of a whole continent. There are three areas that are in particular affected. The first one are the coastal areas. The second one are river valleys. You see the Rhine River, for example, or the Po River. And the third one are always the edges of mountains. You see it here in the Caucasus, on the Carpathian, or in the Alps. For example, in the Alps, you have 12 million people living in the arc of the Alps. But if you take a 40-kilometer wide ribbon along the Alps, there are more than 20 million people living. And then the population density decreases again very rapidly. So we see the highest human impacts always on interfaces: coast, river, terrestrial, and mountains, lowland ecosystems. So humans are, and Hans-Peter has already mentioned it, they are dominating Earth. They are kind of ecological outliers. And I'm just giving two examples of this. One is, these are the humans and 63 species of mammals of about the same biomass than humans. And this would be the CO2 emission, and we see there's orders of magnitude higher the contribution by humans than by other mammals. Here's the second one, and these are humans and more than 500 mammal species. It shows the range size, and again you see humans are this species that dominate the largest proportion of the Earth. If we would add farm animals to this, cattle, sheep, goats, and so on, then we would have an additional group of species that completely dominate the Earth. There was a very stimulating paper a couple of years ago by Peter Kareva from the Nature Conservancy and his co-authors about domesticated nature, and he is showing and describing how we manipulate, optimized, maximized ecosystems for the benefit of humans. And domestication of ecosystems is very similar to what we have the domestication of animals and plants. And we may define domestication by ecosystems that have been optimized or maybe maximized for a few ecosystem services that provide major short-term economic benefits to humans, but often cause unforeseen other changes in ecosystem attributes. Let's take an example from rivers. We can arrange all the rivers. This would be European large rivers, along a gradient of domestication. We don't have any natural rivers anymore in Europe. There are very few near-natural ones. Most of them are highly modified or human-controlled or human-made. In the state of Brandenburg, for example, around Berlin, 70% of all rivers are artificial. These are drainage canals, and this is more or less the same what we saw yesterday in James Switsky's talk about the Indus Valley or the Netherlands. Second example about the kind of how fast we transformed our systems. This would be the Danube River at Vienna. It's about 160 years ago, an air photo from a balloon. You're looking westwards. Here there's the city of Vienna, and here you have a fascinating braided river systems. 40 years later, the whole river had been completely channelized. After the construction of the Suez Canal, they moved the whole heavy equipment that they used to dig up the Suez Canal to the Danube, and within relatively short period, they completely channelized the whole 2,800 kilometers of the Danube River. And this is how it looks today. So the whole, there's nothing, this is a state that cannot be reversed. People have occupied now all the floodplains. In Europe, there's an estimation that 50% of the human population is living on former floodplains. There are data from Japan that 50% of the people and 70% of the assets are located on former floodplains. And these are not just completely modified, new or domesticated ecosystems, they are also more and more colonized by novel communities. If you go to the upper Danube, close to Vienna, and you take a benthic sample today, on average 80% of all individuals are of non-native origin. So you have a community that is composed of natural and non-native species here, a kind of multicultural community that you can find today in these river systems. The same is, of course, on other large rivers like the Rhine River. The Rhine River is a heavily modified river and is a highway for navigation. And for the Rhine River, we have a long-term record of benthic invertebrates. And this is a graph that is very often shown by politicians because it shows that we did a very nice job to recover and restore the Rhine River. So there are benthic invertebrate diversity about 100 years ago at the beginning of the last century. Then you have the very fast decrease of benthic diversity, and then now you have a recovery as well. But what is not said is that the community, again, that you have today has nothing or almost nothing in common anymore of the community that was there 100 years ago. It's about the same picture that you have from the upper Danube with 80% of the individuals of non-native origin. And the second aspect that we have to keep in mind is, at that time, when these samples had been taken, the Rhine River had been already channelized for almost 100 years. So it has been already a very heavily modified system at that time. So we have these domesticated ecosystems and we have novel communities. And there are three key questions that we have to answer as scientists. The first, how do these systems form? How do these communities form? What are the underlying processes, and can we make any prediction what kind of communities we will expect or may expect in 20, 30 years? It's for sure these are not the same communities than we have today, and it's very hard, and I would almost say impossible to make any predictions what kind of communities there will be. What are the ecological, the evolutionary, the economic consequences of communities that have no shared evolutionary history? And what are the consequences for management and restoration? Let's take a second example on this. This would be at the European scale, non-native fish species from 253 catchments, all the primary catchments with more than 3,000 square kilometer catchment area. And this is the number of non-native species within the catchments. So you have up to 25 species in the catchments that are of non-native origin. And you have a high proportion of catchments where you have 40 and up to 60% of the present species pool are of non-native origin. In all these catchments, you have a net gain of species. In average, you have an increase of 5 species per catchment compared to the historic conditions, and we had a benchmark of 1840 for this. And most of these catchments with the highest proportion or highest share of non-native species, they're all located here in the Mediterranean area. There you have, on the one hand, a relatively low native species diversity. On the other hand, you have a very high number of reservoirs that facilitate this kind of spreading of non-native species. So you have an increase of species richness. At the same time, you have an increase of similarity among these catchments, so a kind of homogenization. In average, for all Europe, this is the number of species, 515 fish species, you have 3 percentage points increase in similarity, from about 26 to 29%. And the key contribution to this kind of increase of homogenization is range gain. It's not range loss. and it's the translocation of species, so a range shift and an increase of the range of native species there. I have to add that about 15 species of the European fish pool went globally extinct. So there's within 150 years, quite a lot of species went globally extinct. One reason for this kind of homogenization is that we have now, we are connecting all these rivers through navigation canals and navigable rivers. You can travel today from the Rhine River to Western Siberia without going any more to the sea. We are creating biologically a kind of mega catchments here of more than 2.5 million square kilometers. On the one hand, we are fragmenting the rivers along the rivers by constructing dams, and horizontally we are all connecting these river systems. Let's come back to this picture on the night, Europe during the night. And here this is Berlin. You see this is the city of Berlin, and it's surrounded by quite a dark area. And we were flying Berlin during night with an airplane. So this was a 4-hour flight that we, in strips, flighted, and we created a high-resolution image of Berlin during the night. Just this would be the Brandenburger Gate here, and this would be a dark area here in the middle of the center. This is the brightest spot in Berlin. This is the airport in Tegel. So we have, on the one hand, domesticated ecosystems, novel communities, and we have also novel stressors. So new stressors that are affecting our ecosystems. And one of these stressors is light pollution. Light pollution means the pollution of natural light through artificial light. And this is Berlin again. It's a huge influence. For example, when you have an overcast of the sky here, it amplifies the light pollution. It's 10 times brighter than during clear conditions. It's exactly the reverse. What happens in nature when you have an overcast, it's getting completely dark here. What is the global dimension of light pollution? As an example of a novel stressor, there's a fast increase in light pollution by about 6% globally and up to 20%. The electric power consumption through light pollution, globally it's about 20%. We are just using for lighting areas. And we have almost no knowledge about what the ecological, what the socioeconomic, what the health consequences of completely modifying our nightscape is. So there was a book a couple of years ago by Rich and Lancor, and they stated, what if we woke up one morning only to realize that all of the conservation planning of the last 30 years told only half of the story, the daytime story? If we ignored night and light pollution as an important stressor, would it have influence, or does it influence our conservation planning? I mean, we know that many species are light sensitive. So this would be the light spectra of common lamps, and this would be the kind of light sensitivity of different organismic groups here. We see that each of these groups have a different kind of sensitivity to different light spectra. There's also an evolutionary aspect behind, because nocturnality is a very recent evolutionary development as well. We see this would be the pacel divergence time here, and this would be the proportion of species within individual group that are nocturnal. We see an increase here with recent times here. Again, of about 50% of all species are nocturnal, and there are of course groups that have a high proportion of nocturnality. And there's also a very rapid adaptation to this kind of changes as well. Bats, for example, fast-flying bats, they can rapidly adapt to this change of the nightscape and outcompete, for example, slower-flying bats. This would be major evolutionary effects, but there might be also major ecological consequences as well. These are just two examples of potential consequences. The first one is the kind of vacuum cleaner effect, and the second one would be the crash barrier effect, where light may impede the kind of dispersal of emerging aquatic insects, for example, to the hinterland. We were starting to study this by exposing artificial lights in the landscape. This would be an artificial light here. Here there's a window trap. Here you see an emergence trap. And then we were looking on the effect of such artificial light on the dispersal of aquatic adult and terrestrial insects. So we had then traps at different distances from the shoreline and from the light source. And just one example on this, it's a messy table, but just give you an idea. This would be the pooled number of insects in dark and lit areas over a whole season. So we have always pairwise nights, dark and lit nights. And this would be aquatic tip terrain, for example. You see that you have close to the light, you have orders of magnitude higher catches than if there would be dark nights as well. And you still see an effect about up to 40 meters from the light source away, where you still see an increase in the catches. And the second aspect is that there are differences among different faunal groups as well, so they react differently. That means light pollution also changes the composition, the relative composition of aquatic and terrestrial organisms. So if we take this light pollution, then it's a kind of huge global self-experiment with an unpredictable outcome. It has socioeconomic consequences, health effects, ecological aspects, and technical consequences as well. And we have to see this again within the background of policy. For example, in Europe, they are changing now what kind of lights will be implemented or forbidden without knowing what are all the consequences of light pollution. A difficulty is then to separate the effect of light from other stressors as well. In urban systems, they are interacting. And so one way to study this is to experimentally separate or test the effect of light on ecological and evolutionary processes. Here this is an artificial experimental setup. Here you see the street lamps, here you see emergence traps again, and here this is looking the experimental side, the lit area from an airplane. So this leads then, so this was just one example about this light pollution as a major novel stressor that is influencing all aquatic and terrestrial ecosystems. What kind of management options do we have? We have, again, a whole range of management options, from conservation, restoration, mitigation to intervention. More and more, there is an active way of how we have to replace or complement restoration measurements by pure intervention measures. In Europe, the key legal framework that is controlling how we manage our systems is the Water Framework Directive. It's quite a simple concept. We have to define the ecological status in 5 classes. It's based on the composition of organismic groups, fish, invertebrates, and so on. It's a structural parameters, and then you have a chemical aspect as well. And there are 2 key principles. The first one is to prevent deterioration, and the second one is to enhance or increase quality. So these are the 2 principles. The first thing is that is critical is that the deterioration principle must have a higher priority than the restoration principle. This is one of the first aspects that we have to consider. But there are key strengths and weaknesses of this European Water Framework Directive. The strength is that ecology has been put to the fore. The second is there's a catchment approach, there's basin management plans, participatory approaches, and there's an establishment of a network of monitoring sites which provide fascinating, consistent data across whole Europe. But it's primarily a structure-based concept. It's looking on species composition, chemical status, and only on the river channel. And there are some weaknesses. The first one is, and the most difficult one is, to define reference conditions. And how can we use, based on the structural composition of species, the past conditions as a goal for future ecosystem management if you never will get the communities back as they had been before. And the second major weaknesses is that it competes with more human-oriented objectives of the European Union legislation, climate, flood, agriculture. And it's clear, when there is a competition, environment is the first that loses. I'm coming back to this in a second. About 90% of all rivers in Germany do not achieve at the moment or do not have a good ecological status. So these are the rivers that need or should need to achieve a good ecological status. These are thousands, 10,000s of kilometers of rivers that would need to be restored. This would be just the large rivers here, and this would show the probability to achieve a good ecological status by 2015. Red means it's impossible, more or less, and we will not, based on this legislation, reach a good ecological status. And we would need to set priorities, where to start in respect to this restoration. One way is that we are looking not only on structural aspects, that we are looking much more on kind of functional processes. And one functional process in rivers that is very critical would be to allow successional processes, for example. The development of a whole range from early succession to late succession. And one aspect or one element of this would be vegetated islands, riparian, in-stream riparian sounds here. This would be a formation, recent formation after a flood event where you see a whole range of successional stages that they're allowed to develop. So we looked on islands, vegetated islands along European rivers, and it's looked on the present composition or the present distribution of islands. This would be along the Danube River, from the source to the mouth here. You see this increase in size, and you see two areas in the middle and in the lower part where you still have quite a high number of vegetated islands. This would be the Rhine River, and both Danube and Rhine, we have also historic maps as well, so we can show how much islands did we lose due to regulation. It's about 90%, and many of the islands that we find today there, they are all regulated or channelized. So one, in respect to prioritization and to management, is to allow processes. And one of the easiest way to allow processes is, for example, to do nothing. For example, no maintenance work as well. This is from the Alluvial Sound National Park in the Danube. When they created the national park, it was not allowed anymore to remove dead wood. And not to remove dead wood created a huge complexity of the whole system. This was the best restoration projects I saw along larger rivers over the last 20 years. And these large wood deposits are then also responsible for the formation of these vegetated islands, for example. So this would be a sketch. It looks here there's a stranding of a tree, you have sedimentation, you have scouring, then you have the formation of an island, and at the end you have a fascinating complex mosaic of aquatic and terrestrial ecosystems that are linked to each other. So these islands might be pivotal landscape elements that reflect functional diversity and can be used as indicators. So they may increase the resistance and resilience along a river system, providing refuge and major habitats for aquatic and terrestrial systems. They are major sites for the input of high labor organic material. They can be islands of fertility, as they have been described for more desert areas, and they may be important landscape level indicators. So I focus much more on processes, on functions, than on structural components in assessing river systems. The second, this would be on the global scale, important direction we are facing is this IPBS and this intergovernmental platform on biodiversity and ecosystem services. And what is related to this is this deep study where it's the economics of biodiversity and ecosystems. So there's a strong focus at the moment on ecosystem services. But I think there are two shortcomings on this ecosystem service concept. That is a fascinating, excellent concept, but at the end we see it's primarily focused on the economic valuation of the services. This is one of the big shortcomings. And the second one is that this close link between biodiversity and ecosystem services, and very often you don't see a clear relationship between biodiversity and ecosystem services, which means that at the end we can live with a relatively low biodiversity by maintaining the same ecosystem services. Just to take 2 slides on this. It's not a simple relationship between biodiversity change and functional change. There's environmental change that influences directly or indirectly functional change, and it is a scientific challenge to understand what is the contribution of biodiversity to changes in functional changes along a kind of environmental change gradient. And there was a very excellent paper recently here by Hooper et al. That demonstrates the kind of productivity as a response. This would be biodiversity, and this would be the environmental factors. We all know when biodiversity, species richness goes down, that you have a decrease in productivity. This is about the same decrease that you may have if you have a natural environmental factor like drought. But at the same time, if you change the environmental conditions, if you fertilize this, of course you can compensate this loss and overcompensate this major loss. And this is leading to my last point here, because this is going back to this kind of changes in the environment due, for example, the implementation of an energy transformation phase, the so-called Energiewende in Germany, where they implemented within a very short period. There was a window of opportunity where they started to change the whole energy policy there as well. And this was related to Fukushima as well, where they stopped nuclear power plants or nuclear power production in Germany. But there was a second major reason for this kind of Energiewende or energy transformation. It was a pure kind of economic reason to be ahead of a few years in the kind of innovative development of tools and in the industry globally in this market of renewable energy. This was the major motivation for this energy transformation. And this has been implemented at a large scale without looking on what are the consequences for ecology, for social systems, for the environment. The one is we are facing at the moment in Germany, in Europe, and large parts in the world, the fastest change in land use. You see due to this biofuel construction, you see in Germany whole landscapes that are completely transformed now, and they are just used for maize production. And the second major boom that we are experiencing at the moment is a huge boom in hydropower production. Globally, in Europe, in Central Europe, it's difficult because the best places are already exploited. There's a boom in small hydropower plants, which do not contribute a lot to the energy production, but disproportionately use environmental resources in the way of free-flowing sections. You have seen this slide yesterday about the existing hydropower dams globally. We had the last year or so, we were sitting down and we were collecting information about all the plant and all the hydropower plants that are under construction. And these are just a large one. There's about 2,000 hydropower plants that are in planning or under construction. You have clear hot spots here. The Amazon, whole Africa, the Balkan, the Caucasus, the Himalayan, or for example the Amur Basin here. So we are complementing this area. This is the existing one, and now we are adding to highly sensitive areas. We are highlighting a huge amount of new hydropower plants. Again, the whole planning has been done without, I'm not sure how many scientists who are in these societies had been involved in this kind of planning of these hydropower plants. It's not a question, hydropower or not hydropower, but the key questions from a science point is where to construct them, how to construct them, and how to operate them. And we have to provide clear answers to this, because otherwise there's an uncontrolled construction of hydropower plants here. This would be just in Asia. This would be the existing and the future hydropower plants here under implementation, and the the existing one, different discharge categories, and you see there are orders of magnitude more plants that are existing at the moment there. And the last point I would like to mention here is we have a fascinating global network of infrastructure that is critical for science, for education, and for outreach activities. And these are the role of biological field stations. I'm saying this because we have a very nice, fascinating biological field station at our institute, and this is on Lake Stechlin here. This is the station here, and we have from this lake we have 50 years of records, long-term records about the environmental development as well. And we can combine this, for example, now with experimental facilities as well to understand the underlying mechanisms of this change. This is the lake lab. These are 9-meter diameter each, 20-meter depths, and the sediment is included here, and these are 24 of them, so to really carry out experimental work in a repeated way. And this would be, and we have a global kind of network of biological field stations. This is just an example of 4 countries here: Canada, Russia, Japan, and China. More than 1,500 of terrestrial, marine, and limnological field stations are existing. We know about these situations in Canada and in Europe, that several of them are highly endangered or are getting or becoming closed as well. On the other hand, in other countries, like in China, there's a really boom now in developing biological field stations. But most of these biological field stations are located on very nice, remote natural parks, nature conservation areas. There are very, very few field stations that are really in agricultural or in human-dominated ecosystems as well. So this would be a kind of complementary sites that need to be added to this. But this is a global infrastructure of fundamental importance for education, for science, and for outreach activities. Some final concluding remarks. Rivers and many other ecosystems are domesticated ecosystems. They are formed through and require continuous human input and activities. They are driven by novel stressors, and they contain communities that have no shared evolutionary history. It's a key challenge to forecast which kind of communities we may have in the future and what are the different consequences of these new communities there as well. We have to rethink these management options forever. Reference-based strategy, at least for structural aspects, do not work. And human outside nature approaches also are not appropriate. And the last one is that these conservation efforts, and it's clear the conservation of the last remaining rivers must have the highest priority, but it needs to be complemented or perhaps even replaced by increasing levels of management intervention. And with this, I would like to thank you for your attention.